right, welcome in, everybody. I am getting over a cold, so you'll have to excuse my voice and a little bit of coughing today. Probably will cough numerous times throughout the class. So we'll do what I can here to keep my voice okay. A couple things I wanted to address because honestly, there's not a whole lot of time left in the class. We are basically almost at the end. It's going to seem like tomorrow. It isn't tomorrow, but it's close. So here in a little bit, when we get to the actual math, I'm going to pick up with Chapter 9. I didn't have any students asking me about Chapter 8. No kind of questions or anything, so I guess I'm assuming everyone did okay with it. So if you need to have me look at Chapter 8, send me some stuff. But I feel like probably our time is better spent on Chapter 9, since for most people, that's a pretty confusing topic. Okay, so that's kind of my plan. If you need something different, I have office hours. You can come talk to me, all that kind of stuff. Get the help you need, tutoring center, all those things so that we can get you taken care of so that you understand those topics. With that said, a couple things I want to show you since we're almost at the end here. So from the front page of Ventura College, you get the important calendars. It literally says academic calendar at the top. So on the front page of VC's website, you click that, and it takes you to the page that has a bunch of calendars. So there's the final exam schedule, pretty important, and the instructional calendar, pretty important, right? So I talked about these at the beginning of the semester, but I know that was a few months ago, right? We're talking, 4 months ago, so people forget. But this is one of those little things you can do. There's a lot of little things you can do as a student that help in a big way, right? I think a lot of times students look at something and go, I'm just going to skip that. I can get away with not doing that. But there are some things that only take like a minute to do. And if you do them, they can save you a lot of time and energy down the road. Looking at the calendars and being aware of the calendars is one of those. So 2 calendars you should be very aware of is the final exam schedule / calendar and the instructional calendar. So let's take a look at the instructional calendar first. Let's blow that up. So where are we? Let's see. So we have class up until the 8th. We are a Monday, Wednesday class. So that means we have what? 1, 2, 3, 4 more times that we meet, not including the final, but most of you probably will not actually show up at the final exam time. You'll just take your final and turn it in. I'll talk about that in a few minutes. So that means we have 1, 2, no, let's see. Today's 29th. Yeah, 1, 2, 3, 4 more times to visit, and then your final exam. So I'm starting to get emails about the final exam. Remember, we talked about the final exam at the beginning of the semester. Also, it's mentioned in the syllabus, I believe, under exams. It mentions a final exam in there. So that means we have four more times. So the rest of this semester is going to roll by. We got this week and next, and then you don't even really meet with me directly, right? So I do have office hours this week, and then once final exams start, office hours don't happen at the same time because, some classes have already finished. Well, I'm not going to hold an office hour for a class that's finished. That doesn't make any sense. And the schedules for final exams is just totally different. Your schedules are different. Mine are different. Many of you are moving around work days so you can get your final exam done on time and stuff like that. Just be aware of that. We got 4 more visits. We can talk about stuff. There may be a day to review overall. There may not be. We'll just kind of have to see how it goes for the next couple of weeks. Now, final exams. When's the final exam, right? That's a question. Well, it's right here under calendars, or academic calendar. The school posts the final exam. They used to post it before the semester started, but lately they've been getting it released mid-semester, which is kind of weird because they tell us we're supposed to put the final exam time in our syllabus, but then our syllabuses are due before they release the final exam schedule. So that doesn't make any sense. But right now, even a couple weeks before final exams, you can go figure out when everything is. So you just go to that page, the top of the Ventura College webpage at any page you're on. It's got academic calendar right up here at the top. You click that, and it takes you to this page that has the final exam schedule on it. So you click that, blow it up. Okay, columns are days, rows are times. So you just find, when does your class meet? Well, let's see. We are We are a Monday, Wednesday, 10 a.m. class. Looks like that one's right here. So, unfortunately for you all, it's the last day of finals, so you're going to have to stick around a while or take the test early or whatever. You will be able to take the test early. You can't do anything with it after that. But so Monday, Wednesday at 10 a.m. from 10:15 to 12:15, that's the last moment that you have to take your final exam. The final exam will take place online. It will be similar but a little bit different to the exam you took so far in this course. You will not get a retake for the final exam, right? I can't do that. I would raise some eyebrows from the school if I gave retakes on a final exam in math. But so you only get one shot at it. But you can finish it early. So if you wanted to finish it a few days early, you can. I'll have it posted for probably most of finals week. You'll be able to go in and take it. Just realize once you take that exam, you're done with the course. You can't retake the final or ask more questions and try to get some more points like that. You're done at that point. Okay. But it's up to you. If you know the material at the beginning of the week, then you don't need to wait till Wednesday to take the final exam. You can take it early, and that's perfectly acceptable if you're ready. I don't recommend that you take the test early if studying for another day would help you get a better grade. But you're the only person that really has a sense of how well you know the material. How well am I going to do on the test if I take it now versus what if I spend another day studying and then I take the test? Will that help me? Right? And it sounds like, well, wouldn't that always be the case? Sometimes no. Like if you know the material and you're probably going to get an A, why wait? What's the point? Right? I mean, at some point you know it as well as you're going to know it. That doesn't mean you're going to get 100%. People always make slight mistakes here and there. But if you know the material, take the test and then you can start your break, right? But if you're not, if you need more time, you can wait until this time to take the test. But I will just say, I'm not allowed to take anything after 12:15 p.m. Plus, you've had a week previously to do it, or close to a week, 5-6 days. So if you're turning it at 12:16 p.m., sorry, not going to count. That's school policy, right? They have it in here. Student request for early or late exams. I think I've shown you this before. You have to have a dean's signature before the test. So if you're like, oh, well, my power went out when I was trying to turn it in at 12:15. Sorry, you should have got it in earlier than that. So I highly recommend you don't wait till this time to take it. I always have students that are, 12:14, they're trying to get it in. It's like, okay, they're taking an awfully big gamble right there. It's got to be in because otherwise what happens is students complain and say, well, he let some people turn it in late, but I worked hard to get it done on time. Why should I have to get it in on time when other people were allowed to turn their work in late? And that's pretty reasonable, right? Now, if something comes up where, like twice in the 8 years I've been at Ventura College, I think 2 people were in the hospital during the final exam time, and that's when, you had to show up and take the final exam. So in those cases, those people were given medical exemptions. But now, even then, if you're in the hospital having surgery or something, let me know, and I'll see if it's in the guidelines for incomplete or something like that. I get a lot of requests for incompletes each semester, and like 99.9% of requests for incompletes don't qualify. An incomplete, if you look it up, is for someone who's doing well. Like one of the things we have to do to give an incomplete, the student has to be in good standing at the time that they stopped attending. Right? So what a lot of students do is they have an F in the class because they haven't done any work, and then they start requesting an incomplete from me. Well, literally that's not what an incomplete is for. An incomplete is for if someone is doing well in the class, they have an A or a B or even a C, but you're doing well in the class, and then you have some type of medical emergency, right? I've had, I think both of the times when we gave that medical emergency condition, I think the women were giving birth in the hospital. And so, yeah, if you're supposed to be in a classroom taking a test, but instead you're in the hospital giving birth, okay, I get it. That's pretty explainable, right? I go, yeah, well, you couldn't have been giving birth at the same time you were taking a test. So, yeah, here's your incomplete. That's pretty different than, well, I just kind of didn't take the class seriously and I procrastinated a lot. And so now can you help me out? And the answer is no. We have rules here about getting stuff done on time. And this class has been pretty good by and large. But I'm just trying to inform you because I know the emails that I get at the end of every semester. So I would highly encourage you to at least have this turned in the day before. Say your goal should be Tuesday at 11:59, and then if something goes terribly wrong, then you have the next morning as your backup to save it. But if you're trying to get it in at 12:14 and it doesn't work, now all of a sudden you get a 0 on the test. So, because now it's 12:16 and the window is closed. And considering you're going to have a week to do this, there's not a lot of, there's not, short of a medical accommodation, there's not a whole lot of reasons why you couldn't have gotten it done in that week. It's just you waited till the last second and then something went wrong. That's on you. Okay. So if you have a true medical emergency, feel free to get a hold of me. Everyone else, try to get it done at least the previous day. It's another one of those things where a little bit of effort, a little bit of not procrastinating twice as much can save you a problem later on. I mean, you might be all ready to go. You go to turn this in at 12:14, power goes off. No power at your house. Well, you gotta kind of be aware of that kind of stuff happening. So, plan accordingly, okay? And just know it's even right in here. I can't just tell you like look, bold exceptions. This is not my policy. This is school policy. I can't just tell you like, okay, let's just skip the part of getting the dean's signature and stuff. Like, we can't do that. I have to be able to, every way I interact with students, I have to be able to defend in case there's a complaint or something like that. And one of the ways I can do that is by playing by the rules. So if there's a policy that said you can't turn in stuff late, I got to be able to tell my dean, I didn't accept stuff late, just like the school policy says. So just be aware of that so that you can plan accordingly. Great practice to do, turn stuff in one day ahead of time. I've seen students completely change around their grades just by doing that. Just by whenever something's due, they pretend it's due one day earlier, and so they turn in everything a day earlier, and all of a sudden they start outperforming all these other students. Because other students are trying to get it done at the last minute, and then they don't get it turned in on time, and then since they're rushing, it's not done as well. The students who pretend it's due a day earlier, they're relaxed, they're loose, right? You don't want to be doing math when you're tense and scared and full of anxiety. You want to be doing it when you're loose and relaxed the previous day, where you're like, I can take as long as I want on this because it's not actually due yet, and the results are better. So not a bad little thing to pick up. Just pretend it's due this previous day. That will save some of you from a bad time. So be aware of the final exam, okay? And then be aware of the instructional calendar. Things are getting close here. I do have office hours this week and part of next week. Let's see. I do have a Thursday office hour, but there's no office hours during finals. Now, if you need to get a hold of me for some reason, feel free. If you have a valid reason to talk to me, I can try to set up a Zoom meeting with you so that we can, figure out whatever you need to know, or email me. But, I can set up a Zoom meeting. I can set up an appointment during finals week if you need that. Okay, if there's good reason for that. Okay? All right, so those are two things I wanted to mention. And I always recommend, and I see my students that do really well, they actually follow this advice. At the beginning of the semester, just print these two things. Print the calendar and print the final exam schedule. And I know that seems archaic. You're like, print it? Like with paper and ink? Who uses paper anymore, right? But it's super helpful. I see students that they'll take their binder that they use for the class, and a lot of binders have that where you can slide a piece of paper in there on the front. They'll put that on front, the calendar, and then on the back, the final exam schedule. And you know what? Those students don't screw up dates because they know when school is in session and when it's not in session, and they don't mess up the final exam time because they weren't paying attention to where their final is and stuff like that. So not a bad idea. If you're it's another one of those things. It'll take you a minute to print out these two pieces of paper and put it in your binder, but it could save you hours down the road. Like when students show up to school and there's no class that day because it's a holiday, you just busted up your whole morning coming to school when there was no reason to. So good idea. Have those two things available to you. Okay, where are we now? Let's see. Where am I? Class. Okay, so we're on this last chapter. Um, we're on this last chapter here, and then we're going to take the exam, right? So this chapter is probably the most confusing of the entire course. I found logarithms to be very confusing. Didn't really understand what they were until much, much later. Your logarithms will come up for some of you, especially if you are, say, going to take calculus. You'll end up doing calculus with logarithms, but even there, you can get away with kind of memorizing what you're doing and not really understanding. I mean, I didn't have a full understanding of logarithms until like after calculus, because it's like I could memorize how to use logarithms and I would get the points right, but I didn't get it. So then later on, when I was studying topics that you had to understand what logarithms actually were to make sense of them. Then I had to sit down and really force myself to understand logarithms. So it's confusing because there's those two parts, right? There's the part of trying to get problems right, the mechanics, right? The details of writing things out. Like how do I combine logarithms? How do I expand logarithms? How do I solve a logarithmic equation? All of that stuff is fairly in depth. Like I would say it's a big step up from any of the chapters so far in this course. Not to scare anyone, but for me it was. I mean, it was one of the few things that coming out of algebra, I was like, I can do logarithm problems, but I couldn't explain it to anyone. I just know, I just memorized that you're supposed to do this particular thing. That's not good, right? And I'm kind of sharing that because I think sometimes people get this idea that the reason that they're not learning the conceptual part is because they're just not good at math. And that's not the case, right? I have a PhD in math, and I struggled with the conceptual part of logarithms when I first learned them. And that was because I didn't sit down and force myself to learn that part of things. Partly because you generally learn it at the end of the semester. So that kind of sucks. Like there's not a lot of time. Everyone's tired. You're just trying to figure out how to get the problems right. But you really want to have an understanding of logarithms so that you can understand when they're getting used, right? You can understand what the purpose of the logarithm is. Otherwise, what's the point? Right? What is the point of the thing? And we don't even get into logarithms right away. We have to do 3 pretty intense sessions just to get us ready for logarithms. So we've got composition of functions, which isn't too bad, but it takes a little bit of practice. Inverse functions, which isn't terrible, but again, you got to do a dozen of these or so, and then you're like, okay, I get how to do these. And then exponential functions is like a whole new thing. So quite a few topics, and then we get into logarithms. So there's a lot going on in this chapter, and then I'm sitting here also telling you, don't just memorize how to do this stuff. Also try to have an understanding of it, which is hard, right? It's definitely challenging, but just at least leave yourself open for that. Those of you who are going to end up in calculus, there's no point in learning how to take derivatives of logarithms if you don't really know what the logarithm is, what it means, right? And that's actually a thing about mathematics is the importance of being able to do calculations is kind of going away. Why? Because we have software that will do almost all calculations that you want, right? We'll do it for you. As many of you know, as we've learned in the last couple of years, many students have found lots of ways of cheating online because there's websites and apps and all these things that can do all the calculations. So why is it so important that you as the student can do calculations? Well, it's important for 2 reasons. One is that you shouldn't ever be using a mathematical concept that you don't understand. It leads to lots of mistakes happening. And I don't mean mathematical mistakes. I mean students using the wrong thing at the wrong time because they don't really understand what they're doing, or using it in the wrong way because they don't really understand what they're doing. You're just like, I don't know, I learned this, like these steps to do in my math class, but then it's almost like more dangerous. What's the saying about a little bit of knowledge being like dangerous or something, because you start to think you kind of know what to do and then you do that, but you're doing it at the wrong time. It's not really great. So you want to make sure that you're at least leaving yourself open to work on that conceptual part. Like, what does the logarithm actually mean, right? And then it leads people to make incorrect assumptions sometimes because they don't understand logarithmic scales. So, for instance, earthquakes, and I'll probably I'll return to this example when we get there later. If people aren't given information, they assume that a scale is linear, right? That it's given by a line. So that would be, think of the Richter scale for earthquakes. You go, okay, well, a 5's a little bit more powerful than a 4, and a 6 a little bit more powerful than a 5, and a 7's more powerful than a 7, and an 8's more powerful than or 7, whatever I just said a minute ago. But you kind of assume it's going up in a linear manner, but that would lead you to completely misunderstand the severity of earthquakes, because the earthquake is a logarithmic scale. It's a log 10 scale, which I know you don't understand what that means yet, but I'll clue you in. What it means is that each time you go up one whole number on the Richter scale, that earthquake is 10 times more powerful than one number lower, right? So if you don't understand logarithm scales, and, what was it? A few years ago, we were here in Ventura, we had that, was it a 5.2 or 5.4 or something like that? It took place kind of off the coast a little bit, but if you were in Ventura, like, you felt it, right? I remember I was in that decrepit science building that we were in, and that building has lots of problems, and it was shaking enough that I was actually concerned that, like, part of the building was going to come down, because that building has lots of problems. But it was shaking and creaking and making some loud noises, and then a bunch of us got out to the parking lot. But if you were around for that, I forget how many years ago, maybe 3-4 years now, I don't remember. But if you were in an earthquake, I think it was a 5.4, and you go, oh, well, I was in a 5.4, so like a 6.4, that's just what, like a little bit more powerful than the one I was in? No, it's 10 times more powerful, right? So that's why, like, you look at, when you see these earthquakes from around the world that are like 7s and 8s, and you just see pictures of, like, devastation, like everything's just rubble, nothing's left, and you're kind of like, well, I've been in a 5 something, and that's a 7. What? How could it be like that much more devastating? That's because a 6 is 10 times more powerful than a 5, and a 7 is 10 times more powerful than a 6. So that earthquake that you're looking at was actually like 100 times more powerful than the 5 something that you were in, right? But this kind of understanding is completely missed if you don't understand how logarithms work, because people tend to think it's linear, and they're like, oh, that one was like a little bit worse than the one I was in because it's a 7 and I was in a 5.4, so it can't be that much bigger, right? Yeah, it was like a lot bigger. It's like that's why it just leaves devastation. So those are examples where there are times in the real world where logarithmic scales come up, and those of us who understand logarithms, you watch people just mess it up again and again and again, and they make wrong conclusions. They make incorrect conclusions on the thing they're doing because they don't understand it properly, right? That's what we want to get away from. Okay, that said, let's get into composition of functions. And feel free to ask questions along the way when we're doing stuff. Okay, composition of functions, and then we'll get into inverses. Okay. What is function composition? What does that mean when I say that? Okay, so composition of functions, or what we sometimes refer to as composing two functions, is a new operation you haven't learned yet. So you have a number of operations that you should be fairly familiar with, and you've used them in many different cases. So I'm talking about addition, subtraction, multiplication, and division. So if I give you two numbers and ask you to add them together, you're probably going to be able to do that, right? But you want to keep in mind that you have done this with other mathematical objects as well. You haven't just used those 4 topics for numbers. You've used them for polynomials. You've used them for rational functions. You've used them for expressions and equations that have roots in them. Those are different, right? Adding 5 plus 4 is a little different than adding 2x squared plus 3x squared, right? Once you understand how to do it, you go, okay, I kind of see it now. But notice how those operations are a little bit different in those different settings. Well, that's what happens is whenever we begin to look at a new mathematical object, we have to ask ourselves first, how do I add, subtract, multiply, and divide these things? And then you go on to ask yourself, are there any new operations that we're not familiar with that also can be applied to these? And when it comes to functions, the answer is yes. We have this new operation that we can do called composition. So why haven't we heard about composition in the context of numbers or polynomials or roots or anything like that? And the answer is it doesn't make sense in those topics, right? It doesn't make sense to compose the number 7 and the number 3. You'd go, wait, what does that mean? And I know you don't even know what function composition is yet because I haven't introduced it. But that's what we're doing, is we're taking this new object of functions and realizing that there is a new operation that you are completely unfamiliar with that we can apply to these functions. Okay, so basically what we do is, I can do kind of a very generic version here. If we say I've got an x, we feed it into some function f, and the thing that comes out is f of x. Okay, so sometimes in your book they'll have a nice, pretty graphic of this where it looks like a machine, but this is the basic thing that we do whenever we have a function, right? And you did this earlier in the semester where you were evaluating functions. You were taking a value, you were substituting it in for the variable, and then seeing what it all simplified to, right? And sometimes this piece on the end can also be called the y value. Depending on what we're doing, f of x and y are interchangeable, and so sometimes we prefer one of these over the other. It depends on the particular problem. So what do? We have some function f, and we generally give our functions names, partly because you're going to be getting more and more into problems where there's two functions. In this chapter, we'll be doing this a lot. You have two functions. Well, you're going to mix them up if you don't give them a name. So oftentimes we call a function f. Oftentimes we call a function g. F for function, right? And G for the other function. It can be hugely helpful to name your function after what it is. So, what's a smart guess for what we could call a cost function? Well, why don't I call it C? What's a good letter for the revenue function? How about R? What about profit? Well, you could use P. P is a little tricky because there's a number of words, especially in business, that all start with P. You've got product for the number of products. You've got price. You've got profit. So P can be a little bit tricky, but you can still come up with a name that helps you remember it. That's much better than just calling them F, G, and H, because you're not going to remember that F is my revenue, G is my cost, and H is my profit, right? But if you call them C, R, and P, you're probably not going to mix them up, right? You're probably going to go... You're not going to think that your R function is your cost and your C function is your revenue. You're not going to mix those up, right? So what you do is we have a function and we feed some value x into it, and what comes out has two different names depending on the problem. You can either call it your y value, so you take an x, you feed it into your function, and the thing that comes out is a y, or you can take a value, feed it into your function, and the thing that comes out we'll call f of x. That is, the function has acted on x. Okay? Like I say, depending on which one you use depends on what you're trying to do. Okay? So this isn't anything new. This is the same old stuff you did before. You take a value, you plug it into your function, you get out another value. You take an x, plug it into your function, you get out a y. Okay? We are going to expand that and say, well, what if I had 2 steps in my process and I wanted to feed the output from one function into the other function? Well, that is composition of functions, right? So it looks more like this. So we've got, let me copy this piece. So now we have 2 functions. So what do? Well, I take my value that I want to evaluate, or it could actually be another function. You will do this where you feed functions into functions. Okay, that might sound scary. It's not. Like, most people do fine with composition once they've done a few of these. So what we're going to do is take an x value, plug it into a function g, and then what comes out from there we'll call g of x. Okay, but that's my output. That's like my y value, right? Except we're going to plug that into another function right away. So the output gets plugged into f, and then what comes out is f of g of x. So you can read this from the inside out. I took my x, I plugged it into g of x got plugged into f. Now this is interesting because before, when we were doing operations, it didn't have to happen in a specific order. Like, if you're solving an equation, that has to come into a certain order. But like, if I'm simplifying 2 polynomials and then adding them together, it doesn't matter if I simplify the first polynomial, then simplify the second polynomial and add them together. Or if I simplify the second polynomial, then simplify the first polynomial and add them together. I'm going to get the same answer either way. But notice how here the steps have to be done in a certain order, because I don't know what I'm plugging into this function f until I figured out what came out of function g. So it's really important that you understand that these are happening in stages, and that's actually how you end up with the composition of function in real life. They are extremely common, and it's because we're oftentimes describing things that happen in various steps, right? Okay, so let's look at an example of what this may look like. So let's take, for example, f of x equals 2x squared minus 5x, and we've got a function g, and I'm just using f and g in this case because there's no meaning to these problems. They aren't cost or revenue or anything like that. 3x minus 5. Okay, so I want to compose these 2 functions together. Well, that literally means I'm going to stick one function inside. I'm going to feed one function into the other one and see what's going on, because we've already got the x plugged into g. So now we need to plug it into f of x. So let's see. We could write it this way. What is f of g of x? What is that equal to? Well, you work from the inside out. Okay, I'm going to take x and I'm going to plug it into g. Okay, well, g of x, I've got that right here. So what I'm really doing is taking f and I'm plugging it in. I'm plugging in 3x minus 5. Right? Do you see how? Do you see how all I've done is I've turned the g of x into what g of x is equal to over here? G of x is equal to 3x minus 5, so I've turned g of x into 3x minus 5. So what does this notation mean? This means I'm taking the function f, and what I'm plugging into it is the expression 3x minus 5. Okay, well, what's f? Well, let's go look at the rule for f. F says that whatever gets input into f, we're going to square it, then multiply by 2, and then subtract 5 times the input. Okay, so let's write out what that would mean. Well, I'm taking my input and I'm multiplying it. My input is 3x minus 5, so I'm squaring that and multiplying by 2, and then I'm going to subtract 5 times the input. Oops, I'm going to be off the page here, I think. What if I go over this way? No, there we go. Okay, so see how the x's in my f of x just became the input, which is 3x minus 5. This is the same thing you did when you would just plug 2 into a function. You would just turn all the x's into 2's, right? Well, we're doing that now, except the thing we're plugging in isn't just a number, it's a polynomial. But don't let that throw you off. It's not, like, don't overthink it. It's not a problem. Just simplify it the way you know how to simplify it. So we took our 2x squared minus 5x, and I turned it into this, where the 3x minus 5's were inserted for x. Now I just have to simplify this and see what we get. Okay, well, let's do that. So let's see. This one's actually going to get a little complicated. Let's see. But doable. Everyone in the class should be able to do it. So remember, don't try to do too many steps at once when you're simplifying. So this should end up being what? 9x squared minus 30x plus 25. If I messed that up, let me know. But all I did was FOIL. I did the FOIL in my head, so it's possible I messed it up. But I think that's right. Because we'd get, for the outer, we'd get minus 15x, for the inner, minus 15x, and then plus 25. So that should be right. Okay, but then I've got this, I've got to do my distributive property over here, so that's going to give me my minus 15x plus 25. Oops. Looked like I had a typo right here. Must have double tapped the button. Okay, so we've got this simplified now. And then now it's just a matter of simplifying until we get to that final expression. So if I go through and I multiply, I'm going to get 18x squared minus 60x plus 50. So I'm just distributing that 2 in. Oops, it hasn't updated. Plus 50, and then we have my minus 15x plus 25. Okay. Now you just simplify everything like you simplified other polynomials in previous chapters. Okay, let's bring it all together. And let's do, okay, 18x squared. Okay, then we've got, so minus 60x minus 15x will be minus 75x. And then plus 75, is that right? Okay. If I have a typo, let me know. But the whole key was at the beginning here. You plug one function into the other function and you simplify them. So I think that's our final answer fully simplified. Okay. Now, here's a question for you. Since we have this new operation, and we've now sort of looked at how to use it in terms of functions, well, one of the questions whenever you have a new operation that you should ask yourself is this new operation that we're using, is it commutative? Right? So remember, addition is commutative and multiplication is commutative. Subtraction and division, not commutative. So what does that mean again? It means it doesn't matter what order you perform the operation. 5 times 4 is the same as 4 times 5. 5 plus 4 is the same as 4 plus 5. Okay? Doesn't matter which order you do the operation. But that doesn't work for subtraction and division, right? 5 divided by 4 is not the same as 4 divided by 5. So division is not commutative. Well, looking at this new operation called composition, we go, is it commutative? So do I have to be careful about the order in which I do the operations? And I'm kind of running out of time here, so instead of going through it, I'm going to tell you the answer is it is not commutative. So it's like division, where you have to double check and go, okay, wait, am I subtracting these in the right order? Or if it's division, am I dividing these in the right order? It's the same with composition. If you do your composition in the wrong order, you will almost always get a different answer. As you'll see when we get into inverses, there's a very special circumstance where it doesn't matter what order you do it, but that's only if the two functions are inverses. Any other time outside of inverses that you try to compose two functions, you're going to get different answers. when you compose them. So if instead, what I'm saying is if instead we tried to figure out what g of f of x was, so you notice how before we figured out what f of g of x was, that means that we were taking the function g and sticking it in, we were feeding it into the function f. Well, now what we're doing here is I'm taking the function f and I'm feeding it into the function g. Okay, and like I say, I was going to go through this, but for time, I'll skip it. I'll just give you the answer. If you figure out what g of f of x is, you're not going to get this thing we got up here. You're going to get a different answer. Okay, so that means you have to be careful with your compositions. And in fact, where's the section on? Somehow I'm missing an assignment here. I might have to add a couple things in here. But I forget how they do compositions. Composition has another notation, which is, to me, outdated and shouldn't really be used much anymore, and books are moving away from it. But I forget how they do it on Delta Math, and that is that you have this other way of doing it. I think it's less intuitive. Oh, weird, it's not. I thought I knew what the code was for this symbol, but apparently I have forgotten. It's not rendering it right. Let me look it up really quick. Oh, it's not slash circle, it's slash circ. I knew it was something like that. There we go. So it looks like this. So you may see that sometimes. It's just a weird way of writing compositions. In my opinion, it's outdated. I like this because you can just read it. Well, I took an X, I fed it into F, and then I fed that into G. Here, sometimes, like certain books, will leave it backwards so that you're not sure what the order is. So you'll see me most of the time use this notation up here just because I think it's I would make the argument it's a superior notation. A lot of times people are like, notation's notation, who cares? Well, if it communicates the idea better, it's a better notation. So if you see the thing with the circle, don't panic. Just read how they have it work there. Okay. Let's see where we got a couple minutes. So yeah, so just be aware of that. But I prefer to use this notation up here. So it's just your composition. You're feeding one function into the other. And like I say, the first one or two times you do it, it's going to seem super weird. And then all of a sudden you're like, okay, I get it. This is pretty easy. Those of you who are going on into calculus, this will be a very important concept. You are going to have to break functions down into their composition pieces. So you might take something that has a square and a polynomial in it, and you make one function the squaring function, one the composition. You have to break stuff down that way in calculus a lot. You do it a little bit in pre-calc. So composition is kind of something we're learning right here at the end, but those of you who are going on to calculus will definitely be using composition in the future. Okay. Yeah, so that's pretty much puts us out of time. There's no way I can start a whole new major topic right here with 5 minutes left. I can't even start talking about like inverse functions. So I think on one of these assignments, I'm going to have to add a few more problems. It won't be much, but I'll have to add a few things because it looks like something's missing. Somehow I did that. For this semester, I had to recreate all the homework assignments, and so occasionally I missed the topic. Yeah, so that's a good question, and no, I'm just going to go into one of the existing assignments, and I'm going to add just a couple of these like subsections. So it's not like a whole new assignment. It'll be like probably this inverse assignment will have like maybe one or two extra things in it. So it won't be a whole new big thing. It'll just be a little chance for you to like practice that composition that we're looking at because it relates to inverse functions. Okay. So not a whole new assignment, and I'll do that right after class. Actually, let me make a note. Okay. Final. I think that's right. I think the late homework is due like at before finals week starts. So there's a question about when you have to work on the past due homework. I think you have until the regular class sessions. I'd have to double check, but I think it does not extend into finals week, because for finals week I have to start prepping all the classes and trying to get all the grades where they need to be so that I can finalize grades at the end of the semester. So I think you have maybe until like December 7th or something to do any past due assignments that you still want to work on. Okay. So I think that's a good place to stop. I do have office hours for the next few hours. Anyone who wants to hop into Zoom, and it looks like a bunch of you are already here. Anyone who wants to hang out in Zoom and ask me any kind of questions, let's talk about it. Let's whatever your concerns or questions are, let's get those out of the way so that you're not stressed out about them, and then we'll move on from there. Otherwise, I will see you in a couple days, and